Greetings. Today we're going to learn about double counting. Double counting is one of the two techniques of combinatorial proofs. So let's zoom out for a moment and talk about combinatorial proofs. There are two types. One is called bijective proofs. And we're only going to do a simple example here. Our focus will be on the second type, which would be double counting. For bijective proof, I'll give you one example, and that's n choose r is equal to n choose m minus r. And if you want to prove this algebraically, it's very simple. N choose r, you know that's n factorial over r factorial m minus r factorial. And then n choose m minus r, by definition, is m factorial over m minus r factorial, and then n minus m minus r quantity factorial, and these two are the same. But that's not a combinatorial argument. That's an algebraic argument where you use algebra and arithmetic to establish equivalence. Instead, a combinatorial argument would be looking at something of this situation. N choose r, you can think of as having n slots, and then you choose r of them. How many ways can you choose r of the n slots? Well, that's exactly the binomial coefficient n choose r. But you could also say, instead of choosing r of them to put check marks, you'll choose the m minus r remaining slots to not put check marks. And therefore, the number of ways to choose m minus r empty slots would be exactly the same as the number of ways to choose r check marked slots. And those two scenarios are in one-to-one correspondence. Anytime you choose 3 check marks, you're exactly choosing m minus 3 of them to not have check marks. So those are in correspondence, and that's called a bijection. For math majors, you will learn about bijections a lot more in abstract algebra. So that's all we're going to do here in this course. You do need to know this result, and we've used it before. The focus today is on double counting. And we'll use an example from a homework problem that you've had before. A while back, you had a homework problem where it has to do with Barbie dolls. And each Barbie doll had r equals 4 phrases that's programmed into the doll. And then as the factory is programming them, they have n equals 269 good phrases that they can choose to use. Is this ringing a bell for some problem that you worked on before? And then there's one bad phrase that you like to not use. So how many good Barbie dolls can we make? Different ones can we make? Well, let's think about all the Barbie dolls we can make, good or bad. So we have m plus 1 phrases, and we're choosing r of them. So this is all possibilities. Now, what are number of good ways to make Barbie dolls? That would be with the n good phrases, and then choose r of them. So of the 269 good phrases, choose 4 of them. So these are good Barbie dolls. If you subtract all Barbie dolls you can make, and with the number of good Barbie dolls you can make, you would get the number of bad ones. And the bad ones are the ones that include the bad phrase. So how many ways can we do that? Well, of the n good phrases, we want to choose 3 of them, not 4, because we know one of them, we choose 3 good phrases, and then we add in the bad phrase to create a bad Barbie doll. So this is something that you might have noticed when you were doing that homework problem a few days ago. There are 2 different ways to do it. One is directly calculate the number of bad Barbie dolls. The other is, because you calculated the number of all Barbie dolls, you can subtract the number of good Barbie dolls. And if we rearrange this, we get that n choose r minus 1 plus n choose r is equal to n plus 1 choose r. And this is Pascal's theorem. And you might have seen Pascal's theorem before in Pascal's triangle in grade school. So if you write these numbers, what are these numbers that I'm writing? These are numbers that you will get if you expand binomial coefficients. Have you seen this Pascal's triangle before? What we're writing over here is, well, 1, 2, 1 is 2 choose 0, 2 choose 1, 2 choose 2. The next row, 1, 3, 3, 1, that's 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. So if I move backwards, this is apparently 1 choose 0, 1 choose 1, and 0 choose 0. Alright, so that's Pascal's triangle. I wasn't quite sure how to start from the top, so that's why I picked a more generic row and then worked backwards. And I'll write, maybe I'll draw out this thing. So what this Pascal's theorem is saying is n choose r minus 1 and n choose r. If you sum them together, it's the next number. So let's pick, for example, the numbers here. That 1, 3, and 4. Well, that's right here. And Pascal's theorem says here the case n is 3 and r is 1, right? So 3 choose 1 minus 1 plus 3 choose 1 is 3 plus 1 choose 1. And similarly, we get the other ones. So these numbers we get, I was able to write these out because I mainly remember them, but also you're adding 2 on the triangle above to get the 1 in the next row, and that's exactly this relationship. So that's Pascal's triangle that sometimes people have encountered in high school. If you're not sure about this, pause this video and think about that before continuing. So this is an example of double counting. That's what we're studying today. Double counting is when we have a situation like counting bad Barbie dolls, and we count it in 2 ways. One is directly, the other is maybe some other way, and then we have an equality. Notice I did not use any of the definition of the binomial coefficients like these, using factorials and then using algebraic manipulations to calculate to establish equality. Instead, I told a story. I described a situation and I counted it in 2 ways. So that would be the algebraic proof, the combinatorial proofs that we'll be working on today. Here's an example of a simple theorem in the textbook, Theorem 5.11. Details are in the textbook, so I'll simply give you a quick rundown of it. So this is a sum, r equals 0 to n of n choose r, and that's equal to 2 to the n. So n choose r, as r goes from 0 to n. So think of that as one row of the Pascal's triangle. So if n is 3, then we'll sum 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So summing across the entire row of Pascal's triangle, for instance, 1, 3, 3, 1, that gives us 8. That's 2 to the 3. So that's 2 to the 3. So you can think of this as, so if you want to do an algebraic proof, you can see how to do that from the textbook. But let's talk about a combinatorial proof. So usually you would give some story. So here, so story. And I'll just say n would be, let's say, number of people. And r would be, let's say, number of volunteers. So if we're in a classroom and there's n of you and it asks for some volunteers, how many different ways can we end up with volunteers? Well, we can say, well, r could be 5 and choose 5 volunteer ways to get 5 volunteers to come up, but maybe the number of volunteers is 4 or 3 or even 0 or even n. And so all of those situations we need to count and then sum them up together. And that's the mutually exclusive task principle. Now we sum up all those different scenarios. On the other hand, instead of choosing 3 volunteers and then choosing 4 volunteers, choosing 5 volunteers, and then summing up all those possibilities, we can simply ask each person, yo, you want to be a volunteer? And it's a yes, no answer. Second person, yes, no. Third person, yes, no. So for n people, you each give a yes, no answer. So that's 2 times 2 times 2 times 2 and so forth. That's the mutually independent task principle to multiply all the 2's together. So that's combinatorial proof right there. Let me do one more example. Theorem 5.13. That's where m plus m choose r. I know m doesn't have that many humps, but I'm going to try to make it look different from my n's. That's equal to sum as I goes from 0 to r, n choose I, times m choose r minus I. And again, you can try to prove this using the definition of binomial coefficients using factorials. We'll tell a story instead. I'll only sketch the proof here. Again, you can see details in the book. So let me just spell it out. Right? We have n plus m things, but it looks like sometimes we have n things, sometimes we have m things. So let's say we have n red labeled balls. Labeled. I want them labeled so they're distinguishable. So n different objects, and then m blue labeled balls. In total, we have m plus m balls, and let's choose r of these. How many ways can we do that? Well, we have n plus m different objects, and we're choosing r of them. See, so this is exactly the left-hand side. We've already counted it one way. So now we'll count this situation a second time. We'll let I denote the number of red balls chosen. How many ways can we do that? Well, if we have n red balls and we're choosing I of them, then the number of ways to do that is n choose I. And you know that we have then to have to choose r total balls. So out of the m blue balls, we need to choose exactly r minus I of them. so that the total balls chosen would be I plus R minus I, which is R, which is the same scenario from before. We need to count the same situation twice. You do not get to change the situation. If you're going to choose R of them, you're going to choose R of them. It's just that now I'm going to tell you, well, I happen to choose I of the red balls, so then you know you chose R minus I of the blue balls. See? And also, because we don't actually know what I is, it's the same scenario as before. We choose R of them. I could be anything. Well, I could be as small as 0 and as big as R. And so that's why we sum through the different situations, because you couldn't have I both be 3 and 7. Yeah? You chose R of the balls. How many red balls did you choose? Perhaps it's 3, perhaps it's 7. It's not going to be 3 and 7 at the same time. So those are mutually exclusive scenarios, and so that's why we can sum them up. So here we're using a multiplication between the two things, because the number of ways you choose the red balls and the number of ways you choose the blue balls, then you multiply them together because they don't affect one another, as long as you had fixed an I value first. Okay? And then you sum over all the different I values. So you're using the independent task principle and also the mutually exclusive task principle. Oh, this ends my mini lecture. Usually I would give you time to work on problems together, and this would be the problem of the day. This is an exercise from the textbook, and I will give you some time to work on it together in groups. And so now instead, I want you to, I'll talk about this a little bit, and then I want you to pause the video and think about that by yourself for a little bit before you watch the rest of the video. So here is a combinatorial identity. Remember trig identities? They're true statement about trig functions. Well, combinatorial identities are true statements about combinatorial stuff. For example, binomial coefficients and factorials and all that. Typically, when we want to prove a combinatorial identity, we might prove it algebraically or combinatorially. Algebraically, it's very simple. You just expand this out using the definition and see if the left side and the right side are equal. Now, we'll focus on the combinatorial proof, which is using a double counting argument. You want to come up with a scenario and count it 2 ways. So I'd like you to pause this video now and think about it for maybe a minute of how you would start. Right? And then once you resume the video, I'm going to give you some hints, and then perhaps you can pause again and think some more. All right, did you pause? Well, anyway, I'm going to continue. So here are some hints. If you have 2n choose 2, then you should think of, I needed 2n objects, different objects, and then I will choose 2 of them. But at the same time, look at the right side. It looks like I'm going to choose 2 things out of n objects, not 2n objects. So it looks like maybe I need 2n objects, but n of them are of some type, and n of them would be some other type. Right? So perhaps we have, so here's the hint, perhaps given n labeled red balls, 1, 2, ... to n, and then also n labeled blue balls, and then the left hand side is very simple. In how many ways? Can we choose 2 of them? So that would be the left hand side, right? We have 2n things right here. And then we're going to choose 2 of them, 2 balls. So I want you to pause again and think about how in this exact same scenario right here, you could get the right hand side by counting it a different way. Again, you have these 2n red and blue balls labeled like that, maybe arranged this way, and you want to choose 2 of them. The simple way to count is simply say, oh, I have 2n things and I'll choose 2 of them. But is there maybe a more complicated way of counting that you would get? the right hand side. So pause the video and think about it for a minute. Alright, I'm going to continue, but I hope that you actually did pause and think. That would be much more effective than continuing without thinking. Okay. So let's say if two balls are the same color, then we have two ways to choose the color. Because it will either be red or blue. And then choose two ways to choose the numbers. Notice that the numbers would not be repeats. And once you chose, in essence, you're choosing one of the two rows. So in two ways, you can do that. Row 1 or row 2. Yeah. Once you fix the row, then you would choose two numbers. Maybe you choose 3 and 7. You wouldn't choose 3 and 3 because you want two different things. So that would be and choose two ways to choose those numbers. And that explains here, right? Why do we multiply the 2 and choose 2? Because these two tasks are independent. However you choose the color, you still have and choose two ways to choose the numbers. And then so you multiply them together. Now, here we had an if. So this is cases, right? The second case would be if the two balls have different colors. If they're different colors, then you don't really need to choose the colors. But there are n ways to choose the red balls. Oh, there are n ways to choose the red ball. And then independent of that, so let me write that in independently. There are n ways to choose a blue ball. And if there are n ways to choose red ball, n ways to choose blue ball, and those choices are independent, then you know that you can multiply them together. So then that's when you get, I can barely fit this in. Sorry, right here, n squared. And then those two cases, we sum them up because you are either in this first case where the two balls are the same color, or in the second case when the two balls are different colors. You know, they're disjoint, mutually exclusive. So then we add those together. So again, this gives us that 2 and choose 2. This is the direct counting, or you choose one of the colors and then choose two balls of the same color, or you choose a red ball and then you choose a blue ball. And so then that is the combinatorial argument. So we're done. So in my view, combinatorial proofs are one of the most beautiful kinds of proofs, where you're almost not doing any math to the way that you think you usually do math. Not really working with equations, but concocting stories. And in the homework tonight, there will be a lot of concocting stories about balls. Okay, and your balls are probably often labeled with different colors, and then you can pick the number of them. Let me finish by saying algebraic proof, I know I skipped over this, but it's very simple. Yeah, 2n choose 2, you know by definition that's 2n times 2n minus 1 over 2. Yeah. And then over here, n choose 2 is n times n minus 1 over 2 times 2 plus n squared. And the question is, are those two equal? And that's algebraic and kindergarten arithmetic to verify that the two sides are the same. So our focus will mostly be concocting stories and counting them in two different ways. Make sure you do not concoct two separate stories. It needs to be one scenario where you count it in two different methods, and then because it's the same scenario, you'll get equality of your two method. Because even if you approach a problem with two different methods, you should get the same number at the end. And so that's the power of the combinatorial proof. So that's it for today. Bye.